Okay, so this is another video on section 4.1 covering a few other topics in there that we'll need. First off, in the last video we were talking about angles and converting between degrees and radians, and angles in standard position, their initial side, their terminal side, and all of that. You do need to know all of that terminology because now we want to look at what's called coterminal angles. Angles that are coterminal have the same terminal side. What that means is, if I draw one angle in standard position, say right here, call it theta. If I can find another angle in standard position with the same terminal side, then that angle will be coterminal with theta. Obviously, I could do the exact same angle, but then it's the exact same angle theta, and it's not really different, so it doesn't really say anything. But what we can do, since angles work in a circular manner, I could take my angle and start right here, and then I can circle all the way around the entire circle, and then go there, and have my angle finish here. Now that angle starts at the same spot and ends at the same spot, so these two angles will be coterminal. And essentially the idea is, when we start talking about angles in a circular manner, like we're doing here, then your circles can keep on spinning as much as you want, over and over and over and over again. We'll look at an example or two in a minute. You could also spin backwards if you wanted. I'm going to run out of colors with my markers. But if I drew an angle right here, if I wanted, I could spin this way, opposite direction. And now this angle right here would be coterminal with my original theta, because it starts at the same spot and ends at the same spot. We're going to mess around with that a little bit just to make sure we're clear on how it works, and maybe we'll put some numbers in there to make it more obvious. So suppose I have an angle right here, and we'll say theta equals 40 degrees. I want to find an angle coterminal with that. So we already said one thing I can do is start at the same spot, go completely around the circle, and then finish here. Call this angle in blue omega. Well, how big is omega? We said the measure of a circle is 360 degrees. So if I start here, I go all the way around the circle, that's 360 degrees. And then I have to go 40 degrees more to get to this angle. So that's actually 400 degrees. You could keep on doing the same thing. Suppose spinning once isn't enough. You could spin 2, 3, 4, 500 times, as many as you want. As far as figuring out how to get an angle out of that, well, every time you spin, you just add 360 degrees. So if you spin once, take your original angle and add 360, spin twice, add another 360, spin again, add another 360, and you immediately get a whole lot of angles that are coterminal. But the other way we can do it, we said we could spin backwards. So suppose I have my same theta equal to 40 degrees. Now suppose I start here, but I spin backwards to end up there. Call that omega again. What angle is that? As far as it goes when we're measuring our angles, angles are done in a counterclockwise direction. So if I start here in my standard position, if I go counterclockwise, my angles are positive. If I want to go counterclockwise, well, I just make my angles negative. And then what angle is that? Well, if the whole circle measures 360 degrees, and this part of it is 40 degrees, this part has to be 360 minus 40, which is 320 degrees. So it's 320 degrees, but since we went in a clockwise direction, it's negative, so it's negative 320 degrees. And again, by the same token, you could keep on spinning in the reverse direction. Go all the way around again, you would just add 360 to this, add negative 360 to it, and you get negative 680. and so on and so forth. So we see that there's a lot of these coterminal angles out there. We are going to mess around with them and find different things that are coterminal for different reasons. So just keep the idea in your head, mess around with it, come up with positive and negative coterminal angles. Okay, one more application we want to look at. As far as it goes, we were talking about degrees in the last video, in degrees and minutes and seconds and all of that. And one of the ways you see that is when you're talking about latitude and longitude. If you have not worked with latitude and longitude before, essentially latitude lines are lines that go horizontally around the Earth, like this. That one is not very straight. Right in the center, we'll say for the purposes of this right there, you have the equator. And then you can go north of the equator and south of the equator, and those are your measures in degrees, minutes, and seconds for your latitude. 10 degrees north, 20 degrees south, and so on. Longitude measures east and west, and they go this way. You have what's called the prime meridian in the middle. And you go east of the prime meridian and west of the prime meridian. And in that way you can locate any point on Earth. Suppose, we'll just draw a few latitude, longitude lines. Suppose you have some city, say right here. If I want to locate that, well, if this is my equator, I figure out how far north it is of the equator. If this is my prime meridian, I figure out how far east it is of the prime meridian. And when I combine those two measurements, I'll end up right at that point. So maybe for the purposes of this, we'll say that that is 20 degrees, 14 minutes, and 12 seconds north. And 17 degrees, 18 minutes, 37 seconds east. That tells me how far to go north of the equator this way, how far east to go of the prime meridian this way, and when I combine those two, I end up at that point. We're going to use that in a second with our idea of angles to kind of do a nice little example. One thing I would point out, and I'm assuming you all have your book, you should. When you normally see latitude and longitude lines are drawn like I did horizontally. Longitude lines are drawn vertically. And that's how you learn them or whatever. If you look in your book, they actually have them opposite. They have, they have the lines going this way, the vertical lines, as latitude lines. And the longitude ones are horizontal. It doesn't, to a certain extent, it doesn't really matter which way you draw your lines as long as you understand what you're doing. For the purposes of this, we're going to think about it more like this, like the way your book draws it, for the purposes of the problems we're going to be solving. And we'll see why in a second. Suppose, for the sake of argument, let's see. We have our planet Earth right here. And suppose we have some point A, which is at, we'll use round numbers just for this, 40 degrees north and 50 degrees west. Well, if I wanted to roughly plot the point, if that's the equator, 40 degrees north is this way, 50 degrees west is over here, and we'll say that's A right there. Now suppose I have point B. We'll say point B is 20 degrees south, 50 degrees west. Well, that would be, let's see, if this is my equator, 20 degrees south is down, 50 degrees west is the same distance over here, and I end up right there. And that's B. And essentially, since these have the same longitude angle, 50 degrees west, these 2 points are actually directly north-south of each other. Pretty easy to see right here. They're about 60 degrees apart if you do it really quickly. But once we have that, well, we can actually maybe figure out how far apart those points are. The problem is, all of you have taken 171, and you know the distance formula. It's essentially the Pythagorean theorem solved out. But that only works in 2 dimensions when things are flat. Earth is not flat, it's curved, which means we need a different formula to actually calculate this out. But there's a formula for what's called arc length. The arc length formula is S, which stands for arc length, is R times theta, where theta is your angle in radians. So for the sake of argument, just to do this one really fast, we have these 2 points. We want to find the length of the arc between them, so it'll look something like that. Well, the formula says S equals R times theta. Well, what's my angle theta? Well, if you think about it, if this is, say, the center of Earth, that angle right there for A is 40 degrees north. That angle for B is 20 degrees south. So how long is the angle between them? 60 degrees. So theta equals 60 degrees. But in order to use it in this formula, it has to be given in radians. So we convert really quickly to radians. Let's see. We said 60 degrees. The conversion factor, 180 degrees is pi radians. We want to get rid of degrees, so we put 180 degrees on bottom, pi radians on top. Degrees cancel. 60 over 180 becomes 1/3. So we're left with pi over 3 radians. So S is equal to R times pi over 3. The last thing we need to actually solve this out is, in this case, since we're talking about Earth, the radius of Earth. And as it turns out, you can Google this and look it up, the radius of Earth is about 3,960 miles. And now there we go. We have the radius of a circle, and we have the degree measure, or the measure of the angle in radians. Multiply them together, and we can get the length of the arc, which is essentially the distance on planet Earth between those 2 points. If you have any questions about these videos and the stuff we covered, feel free to either mention it in Blackboard on the discussion board under the discussion heading I did for videos, or email me. Like I had said, I'm going to make some videos this way with a whiteboard and me standing here drawing it all out. And then I might make videos a different way using Camtasia software. And you guys can let me know which one you prefer, which one works better or worse, whatever. Just let me know.